Welcome to The Explainer. Today, we are diving into a real scientific detective story. You see, for years, our best virtual models of the sun had this mysterious bug, a flaw that was holding back our ability to predict things like space weather. And fixing it wasn't just about tweaking some code, it was about unlocking a much deeper understanding of our star itself.
So think about it. How do you study the sun? You can't exactly go there and take a sample. So instead, scientists build these incredible virtual suns inside supercomputers. The goal is to predict really important stuff, like dangerous solar flares. But there was a huge problem. For years, these models had a fundamental flaw. Their virtual suns were, well, leaking magnetic energy from the surface, which is something the real sun just doesn't do. To figure out where this leak was coming from, we first have to kind of pop the hood and look inside. So how on earth do you even begin to model the sun's incredible magnetic engine? Well, it all comes down to something called dynamo models. You can think of them as this incredibly complex recipe, a set of equations trying to replicate the chaotic, churning plasma deep inside the sun that creates its massive magnetic field. It is a monumental task. I mean, you're literally trying to bottle a star inside a computer. Now, the leading theory for how this all works is called the Babcock-Leighton model, or BL model for short. What makes this model so powerful is that it's actually guided by what we can see from Earth. It basically says that all the action on the sun's surface, sunspots emerging, twisting, and disappearing, is what generates the sun's main north-south magnetic field. And that field is what drives the entire 11-year solar cycle. So in this model, the surface is absolutely everything. And that brings us right to the heart of the mystery. Because for years, these powerful models, which rely so heavily on the sun's surface, had this persistent flaw, this leak right at that all-important boundary. Okay, to really understand this leak, we need to talk about a concept called boundary conditions. Let's use an analogy. If your simulation is a swimming pool, the boundary conditions are the rules for what happens when a wave hits the wall. Does it bounce off? Does it get absorbed? For our virtual sun, the boundary condition defines the rules for the magnetic field right at the surface. And this is where a major scientific contradiction popped up. You see, scientists had a much simpler model that only simulated the sun's surface. And that simpler model worked perfectly. It showed that the surface should act like a sealed container for magnetic energy. So the big question was, why were the big, complex, full sun models built with a leak in the first place? The evidence from these simpler models was just piling up. And as this quote from the source paper makes really clear, the scientific consensus was shifting. To make the big, complex dynamo models behave like the real sun, they knew they had to find a way to plug that magnetic leak at the surface. So the question became, how do you fix a leaky virtual sun? Well, for a while, the solution wasn't really a true fix. It was more of a patch, a workaround. And this lays out the two approaches perfectly. The old fix was this artificial pumping force that just shoved the leaking magnetic field back down into the sun. The analogy is great. It's like constantly pumping air into a leaky tire. Sure, it works, but it's not a real solution. The new fix, on the other hand, was way more elegant. Rewrite the rules to build a tire that doesn't leak in the first place. But here's the thing about a patch. While it stopped the main leak, it created new ones. This pumping fix wasn't actually based on real physics, and it forced the model to behave in ways that were just plain unrealistic. For example, it made the surface magnetic field purely vertical, which is not at all what we observe on the real sun. This is the breakthrough. The new fix wasn't just some clever patch. It was a correction derived directly from the fundamental source code of solar physics, something called the magnetohydrodynamic induction equation. It wasn't an add-on. It was just a more accurate fundamental rule for the entire simulation. But of course, a new rule is just a theory until you test it. So the scientists set up a kind of virtual showdown to see how this new, elegant solution would actually perform under pressure. So they set up this brilliant head-to-head test. They created a single magnetic region, think of it like a big sunspot group, and put it into 3 different virtual suns, one with the original leaky rule, one with the old pumping patch, and one with the new, elegant fix. Then they hit play and watched for 10 simulated years to see what would happen. First up, the original leaky model, and it was a complete failure. The magnetic fields just kind of drifted apart, canceled each other out, and decayed into nothing. That is definitely not what the real sun does.
Okay, next, the model with the old pumping fix. And you know what? It works. The patch does its job. The magnetic field behaves just as expected, spreading out and creating the stable magnetic fields at the sun's poles that we see in reality. And finally, the star of the show, the new model with its elegant fix. And the result? It worked perfectly. It produced a realistic magnetic field that was almost identical to the old fix. But, and this is the key, it did it without any artificial patches. It didn't need a patch because its physics were right from the start. This chart just shows the results in stark numbers. Look at the polar field strength after 10 years. The leaky model is flatlined, near zero, but both the old pump fix and the new elegant model maintain a strong field of about 3 Gauss. They get the exact same results, but the new model does it more cleanly and based on better physics. Okay, but proving it works on one little magnetic region is one thing. The real test, the final boss, was to apply this new rule to a full-blown simulation of the entire sun, running through its complete magnetic cycle over many years. And the result was a massive success. The model passed with flying colors. It correctly reproduced the fundamental features of the solar cycle, including the famous butterfly diagram, which shows how sunspots migrate towards the equator over each 11-year cycle. It worked. So you might be thinking, okay, cool, they fixed a bug in a computer program. Why is this such a big deal? Well, it's about so much more than that. It's about building a more reliable and physically accurate foundation for all of solar science. This new rule has 2 huge advantages. First, it just simplifies the physics. It's Occam's razor in action. You get rid of an unnecessary artificial piece of the puzzle. And second, and this is maybe even more important, it allows the virtual sun to have a much more realistic surface, one where the magnetic field isn't forced to be purely vertical, which actually matches what we see. And this is why it matters so much. A more perfect virtual sun isn't just an academic exercise, it is a vital tool. Better models lead directly to better space weather forecasts, a deeper understanding of those dangerous solar flares, and it even gives us a new lens to study the magnetic lives of countless other stars out there in the universe. You know, this breakthrough is such a powerful reminder that in science, sometimes the biggest leaps forward can come from fixing what seem like the smallest flaws. And it leaves us with a really thrilling question. Now that we can build a more perfect virtual sun, what other stellar secrets are we about to unlock? Thanks for joining this explainer.